This week we're going to look at some more design concepts, looking at entity relationship diagrams or entity relationship modeling. I have to change the name of that when I get it done, but okay, let's see. And there, ready. Okay, now I'm going to use these PowerPoint slides just because some of the diagrams in there are better than I can make on the board. I'm not going to sort of belabor all this. But here's, in 2 seconds, here, ERDs are a design tool. They show the relationship between things in a system. So if we have students and courses and a schedule, doctors, appointments, patients, all those objects in the real world have relationships to each other, right? So and we even talked about this. We showed it when we did SQL. We saw how to do that. ERDs, entity relationship diagrams, allow us to model that in a way that is easy for someone who is not technical to understand. You can understand how doctors relate to appointments and patients relate to appointments. You can show that relationship, and then you can actually use it to create, and sometimes it's unavoidable, to create rules about the data. For example, one rule could be, can you be a patient in a doctor's office and not have an appointment? It depends. When I lived elsewhere, I changed doctors. Doctor says, all right, if you want to schedule an appointment, I'll put you on my patients list. I said, well, no, I can't schedule the appointment today. I'm at work. I can't talk right now. He goes, all right, when you call me back, when you schedule the appointment, I'll put you on my patients list. So in his office, I was not a patient until I scheduled my first appointment. Now, the other doctor's office may have it differently. You can be a patient, even though you haven't been in there yet. So those are rules about the data, how the data relates to each other, and which is right and which is wrong depends. It just all depends on what the preferences are. But sometimes when you make a decision one way, it leads you to other decisions that are already made for you because you're paving the path in a certain way. All right, and we're going to talk about weak entities, strong entities, all kinds of good stuff. All right, so source requirements. This is just when you're analyzing a system. This is typically, if you're trying to create a new system, you use the data from the old system as a basis for where to begin. All right. The elements of ER models are entities. Sometimes some authors call them entity types. They're basically objects. Attributes, or things that make up those entities. Identifiers and relationships. The entity class is, I'm going to skip through this, just show you an example instead. Entity class might be the item, and the fields. This is really the table definition, entity class. Two entity instances would be two records. That's the easiest way I can think of to describe it. Attributes are things like your fields. Identifiers are things that will become your primary keys. Uniqueness, composite keys, you've already seen that stuff. All right. Then different relationships. This is a binary relationship. A supplier provides a quotation for a customer, right? So each supplier can supply more than one quote. So if you're a salesperson and a customer says, can you tell me how much it would cost me to get 5,000 widgets? Do you have them in the warehouse? And you work up a quote, you give that to the customer. Go to the next customer, you do the same thing, and so on and so on. There's a relationship between the supplier or the salesperson and the quote that they produce. They're related. Another relationship, mother and a father to a child. So, and that's what they call a ternary relationship or a three-way relationship, and we'll see more of that. Now, the notations that they're using right now, we're not going to use those notations. We'll see the ones we're going to use in a minute. Now, we've talked about relationships before. One-to-one relationships, right? Typically, although not always, typically when you have like an employee, things that have a one-to-one relationship, the employee has one first name, the employee has one job title, one social security number, one address, one email address. The person has a one-to-one relationship with each one of those pieces of data, and those pieces of data added up describe that person. Typically, the data is all in the same table. There are times when it's not, and I think in this example here, is an example where you could break it apart. You have an employee who has a locker. That locker's in a locker room in a building at an address, and so on. You could, I don't know, you could then say that information does not need to be stored in the employee's table. One-to-many, we've seen these before. We just talked about quotations. Each one of those quotations, you can have many quotations for a particular item. So if I have widgets in my warehouse, and I'm a customer here who wants to know if I have 5,000 available, or I make them a quote, yes, there's 5,000. Go to someone else, they want to know if I had 1,000. Yes, I have 1,000. So I have multiple quotes for the same item. Okay. Another example might be a patient who's one person makes multiple appointments to go see the doctor. I go get a physical this year. Next year I go get another physical. That's 2 appointments. I'm just still the same one person, but it works out so that there's a one-to-many relationship between me, the patient, and the number of appointments that I make. And then the third one is many-to-many, and we talked about this, students and courses. Students can sign up for many courses, right? Typically, a full-time load is 5 courses a semester. Yet each course has many students in it, right? If it was a one-to-many relationship, it would be pretty expensive because each course would have one student in it, or each student would only take one course, and that would be kind of difficult and it would take you forever to get through college. But those relationships tend to need to be broken down into 2 or more one-to-many relationships for them to be workable at all. So, like you have doctors and patients are related. Each doctor sees many patients. Each patient sees many doctors. So by putting the appointments table in the middle, you take one doctor, one patient, and there's one point in time where they meet together. So that each one is a one-to-many relationship with appointments, and that's a way to break up the many-to-many relationship. Another word that we're going to look at, you're going to hear me say, is cardinality, and we have a maximum and a minimum cardinality. And what that means is this. If I don't think I want to use that example. If I have a courses table, and let's go with the appointments. I like the appointments one. If I have an appointments table and I have patients and doctors, I can say for each time I find a patient's information, in the appointments table, I have to. So if I have a patient's ID number in my appointments table, and then the doctor's ID number right next to it, and then Tuesday at 8:15, that's all I have. But to find out who that patient is, how do I do it? Take that ID number, go back to the patient's table, find that ID number. How many patients should I find with that ID number? 1, right? Because that's a foreign key. So I should find 1, and then I find out their first name, their last name, their address, their insurance information, on and on and on. So that one-to-many, that cardinality is I should have a 1 relationship with that ID, and it should be a minimum of 1 and a maximum of 1. So that minimum cardinality is I should find at least 1. The maximum cardinality is I should find only 1. On the other end of the scale, I have a minimum cardinality of patients making appointments. Now, my maximum cardinality is that each patient could make many appointments, right? That's the max. So I could have my physical this year and next year and the year after that. Those are multiple appointments. So the maximum cardinality is many. If it's 2, it's many. If it's even the possibility of 2, it's many. The minimum cardinality goes back to that example that we just talked about. When you make your appointment, I'll put you on my patients list. That says that if I'm a patient in my patients list, I have a minimum cardinality. In the doctor example I gave earlier, was that I had to have at least 1 appointment to be considered a patient. So that's the minimum cardinality for that example. The other option I have is I could say that you can be a patient without an appointment, and so therefore the minimum cardinality for patients making appointments is 0. So I could be a patient in the patients table and not find any of a particular patient in the appointment. So if they've got my patient ID number in the patients table, it is possible to not find it in the appointments table. Let me say that again. It's possible if I have my patient information in the patients table with my patient ID, it's possible that my patient ID will not be found in the appointments table simply because I haven't made an appointment yet. See all those 3? So there's the minimum and maximum cardinalities. I think they have the notations here. Hold on. No, they didn't. I'm going to go scoot down to that. Here it is. There it is. That's what I was looking for. It's easier to talk about when I can show you the diagram. All right, here's the minimum cardinality. So on the right side of this line, there will be a box where the entity is, like patient or appointment. So the minimum cardinality is the one closest to the entity. So the minimum is, in this case, on the right. The maximum is on the, no, excuse me, backwards. Minimum is on the left. Maximum is on the right. Maximum is closest to the entity. So in this case, it's a mandatory 1. I should find, if I find a patient's ID number in my appointments table, I should find 1 and only 1 example of that patient ID in the patients table, because it's the primary key in that table. If I have the doctor that I had that wanted me to be in his patient, that wanted me to have an appointment before making a patient, is a mandatory many. So that says I had to at least have 1 appointment to be considered to be added to the system, but I could have many. I had to have at least 1, but I could have many. So it's called a mandatory many. An optional 1 is, I'm trying to think of an example. Hopefully they'll have one for me. I can't think of one. This says that if I find the information somewhere that relates back to this, I could find a maximum of 1, but I could find none. And I'm trying to think of how that would work in a way. I don't know. We'll come back to that. Which means I could have 0 or 1. And then an optional many, where other doctors say, I'll put you in my patients list, and even though in the appointments table, it's going to show that you have no appointments in there, but you could have many. Does that make sense? Optional many says, I will put you in my patients list, even though you don't have an appointment yet. The mandatory many says, you have to have, when you make your first appointment, I will put you in my patients list. So once you have the appointment, then you're in. So there's the difference. This one says you have to have an appointment to be a patient. This one says you can be a patient without an appointment. Most of them are like that, at the bottom one. Okay? All right. So here's an employee and a skill. Now, the original ER model version, this is an older notation. Yeah, I get it. I understand how this works. This one here the second one, the crow's foot version, crow's foot notation, for me is easier to understand. Because I know, looking at this, that this is a many-to-many relationship, because the max is many on both sides. But then this is an optional many on this side, and this is a mandatory many on this side. So this says, each employee must have a skill. Yeah, I hope so. Why do we hire them if they don't have any skill? And the other one is that not all skills will be possessed by every employee. All right, a weak entity. The best example, they talk about weak and strong entities. The best example I can come up with is, and the simplest one, is this. What room are we in here? We're in CIS 2028. That's the number on this room. Now, at the beginning of the semester, I send out a message saying, our seminars will be held in CIS 2028. What if I just did this? And I said, our seminars will be held in 2028, and didn't put the CIS there. How many 2028s do you think are on this campus? Probably a lot. More than one? Guaranteed there's going to be more than one. I bet you there's a 2028 in the library. That's higher than 2 stories, right? So in Cooper Hall, it's probably got a 2028. Yeah, so this, you have the room, and then you have the building. When you build your database, you probably will have a table of rooms. Related to that, there will be another table of buildings. These will be related this way. Now, each room will be in how many buildings?
Rooms in the building is just one, so mandatory.
Mandatory one, so one and only one. Now, each building can have how many rooms?
A lot, depending on assignment.
It can have 2?
More than
At least 2? So the maximum cardinality is many.
many.
Now, can I have a building that has no rooms?
Building with no room.
Probably not. Just the space in there is by definition is a room. So that will have so even a garage is going to have one room. So here, but this is a weak relationship. It's weak because in order to uniquely identify a room on campus, I have to know what building it's in. So the combination of building and room uniquely identifies the exact room that I'm talking about. So even though these two things are in different tables, I have a table of buildings. Here they all are. And each building has a code, right? A unique code. Our code for this building is CIS. That's a primary key for this building. And then inside CIS, we have a whole bunch of rooms. Each one of them has a number. All the ones that start with 2 are on the second floor, all the ones that start with 3 are on the third floor, and so on. And so all of those numbers are attached. So I have, in here, I would have a building number or building code, and then I would have a room number, and the combination of the two is going to be my primary key. That's a P, by the way. Primary key, right? The combination of building code and room number is unique. So if I send out an email at the beginning of the semester saying our seminars will be in CIS 2028, this is the only room on campus that's CIS 2028. So everybody can find it. This is an example of a weak relationship. It basically says that at the lowest level, this data cannot stand on its own without a relationship to something else. So rooms, having a list of rooms is pretty much useless if you don't have the building number or the building code to go with it. So you need the combination of the building code and the room number in order to uniquely identify each room. All right, so then you have the similar one, building an apartment and product and version. Like if you say, what operating system do you have on your computer? I have Windows. Which Windows? Windows 7, Windows 8, Windows 10. So the version number is, you can say I have Windows, and that gets you closer to the answer. But if you were asking for technical assistance and you called Microsoft, say I've got Windows on my computer, they're like, well, what version are you running so that I can help you? So that, because each one has its different details. And the same with textbooks and editions, whatever edition that each textbook has. All right. More on weak relationships. These are non-identified, in other words, non-primary key identifiers, vehicle and VIN, vehicle and auto manufacturer. You have the manufacturer, make and model, and then the VIN number. But the VIN number is able to identify the vehicle uniquely, your vehicle identification number, but that also, when you have a VIN number, you then know what make and model of the car it is. But, you know, those numbers are like this long, right? And you know, the 11th number in is the manufacturer, and whatever letter it is a Chevy or something. And then there's more information about what day of the week it was made and so on and so forth. But I don't need that. I don't need to know the make and model in order to use the VIN number to identify the car. So if I find a car out here, if I'm not familiar with cars, I can look at the VIN number, and if I do enough research on that VIN number, I can find out who made the car, even though it may not say on the car. Does that make sense? All right. All right. So the difference, if you are defining a strong and weak entity examples, the dotted line, oddly enough, is the strong. The weak ones are the solid lines. Don't know why they did it that way. I would have thought that the weak ones would have been the dotted lines, but no. Okay, associative. This entities also, I would call this like a transaction table. Too sometimes. Here you have a many-to-many relationship between employees and projects. If you are in a project-oriented workplace, and as an employee, chances are throughout your career you'll work on more than one project, right? On the other side of the coin, each project will have more than one person on it, or the potential for that. So you have a many-to-many relationship. So what they did in here is they put in an employee project assignment table. So whenever you're assigned to a project, we'll have a record of that here. Here's all the list of possible projects you could be on. We'll put whatever project you are in that assignment table, and then your employee number will go in there too. The combination of your employee number and the project ID would be unique. That would be your primary key. And then you record like your hours worked or begin date and end date and whatever other information they would want to have. Here's the other thing. You can have employee selling inventory. Employee table, and then replace the project table with inventory. In the middle, sales. Doctor, appointment, patient. See that? These are very common. And typically, whenever you have a business application, it more times than not, you will have some kind of transaction, a way to make money, right? And that will be, you'll have other tables related to it. Employees making sales. What are they selling? They're selling a list of services, or they're selling inventory, or And then sometimes you have a list of customers, like employees. So, if you go out and buy a car, chances are they're going to keep your name because they're going to fill out that big long contract for the car. They're going to have your name there. They're going to know that you're one of their customers. You call in. They know who sold you that car. They know what car you bought. They know where you live. They know all that stuff. All that stuff is put in different tables. So they have a sales transaction that draws in an employee who sold you the car, the customer who bought the car you bought, the location of the dealership, whatever, it might be another one. Your book calls that an associative entity. It's a way of making an association between two things. All right, subtypes. Have you taken object-oriented programming or any C++, Java? Yeah? You did object-oriented stuff? Okay. Remember when we talked about inheritance? So that's an is-a relationship where a part-time student is a student. A graduate student is a student. A salaried employee is an employee. So you create the object at the lowest level, the salary level, to describe the employee. So you have some information at the low level and some information at the high level. At the employee level, every employee has an employee number, first name, last name, social security number, email address. All that stuff is common to all employees. How they're paid is different. So a salaried employee gets paid differently than an hourly employee gets paid than a commission gets paid different than a volunteer. Volunteers don't get paid. So at the lowest level, you can have multiple types of that employee. But those multiple types are all required because at the employee level, unless you pay everybody exactly the same way, that information is not going to be up there. So you need a relationship, sort of a vertical relationship between what they call the supertype and the subtype. Here's student, and you have undergraduate and graduate. Now, here's the notation they use here is this way. On my student example for graduate and undergraduate, the circle with the cross in it, circle with the cross in it says that you must pick one or the other. You're going to pick one or the other. And the line says that if you pick one, you cannot pick the other. So this is an exclusive subtype with a discriminator. This says, I have to pick one. Well, think about it. If you're a student, you're either an undergraduate student or you're a graduate student. Can't be both, and you can't really be neither. You know, whatever course you sign up for pretty much puts you in that pigeonhole of whichever, you know, if you take a graduate course, you're a graduate student. If you take an undergraduate course, you're an undergraduate student. You can't be both. Whichever one you pick, probably would say, if you take a graduate course and an undergraduate course, you're probably going to be considered a graduate student because that's just sort of the highest level you got to so far. So this designation, the circle with the cross in it, and the line underneath it says that if you pick one, you cannot pick the other, and you have to pick one or the other. So it's exclusive subtypes. In other words, one excludes the other, and with a discriminator, which means that it must be one or the other. Now here, the second one, student, hiking club, sailing club, this says that if I'm in, well, I can be in both, so I don't know what that line, maybe I misinterpreted that line, but with my hiking club, I can be a student and I can be in the hiking club and I can be in the sailing club and I can be in both. Or I could be in none of them. So that this relationship here, this subtype, supertype, is different than the first one. This one's exclusive. I think what they're trying to say here is this one's exclusive, that if you're one, you can't be the other. I would go so farther and say that you have to be one or the other. And this one here is you could be both or neither. Okay? All right. Oh, I like this one. This one's clever. I used to teach database to a graduate school, an MBA program. I used to put this on the board and just let the students talk and figure out what this thing really was. It's called a recursive relationship. I'm going to use a different one. Okay. Oops. Oh, erased the whole thing. It's all right. If I have an employee table, okay, part of what I have in here is I have an employee ID. And that's my primary key, right? Then in here I also have a supervisor ID. And that is a foreign key in the same table. The cardinality for this is if I have an employee ID, we should have one, maximum of one, a minimum of 0. And for here, supervisor ID, I have possible many and at least one. Is that how they did it over there? It's a different example. I'm making my own rules up. My class, I'll make the rules any way I want. What the heck is going on here?
Supervisor can be multiple employers and only supervisor can be one.
So each employee has how many supervisors?
One supervisor.
One. How come I left the minimum cardinality as 0?
All employees.
The minimum says the maximum is 1. And by the way, that's a good thing. Having only one boss, because if you have two bosses, you're not going to please either of them. But who in the company could have no boss?
The CEO itself.
CEO or the owner, all right? So there is the possibility that there is somebody at the top of this pyramid who doesn't really answer to a boss in the traditional way that we think of a boss answering. So I could have a 0 here. Now, the supervisor ID to employee ID. If you're a supervisor, what's the minimum number of employees you're going to have?
At least one.
You got to have at least one. And the maximum, could it be 2 or more? Maximum is many. Here's the thing. If as a sample of the data, if this was my employee ID was number 1, 2, 3, 4, 5, and then this down here is 2, 3, 4, 5, 6. That's 5, 6. These two things are very similar. Why?
Just number of tiers. Employee ID, supervisor ID.
Let me ask you a question. Is your supervisor an employee?
Yes, it is.
Does that person have an employee ID?
Should be assigned one, yes.
Yes. So my supervisor is Mary down the hall, and her supervisor ID is 2, 3, 4, 5, 6. That also happens to be her employee ID. So if I had a list of, if I had a employee table, let me do it over here. If I had an employee table, and I have an employee ID, I have 1, 2, 3, 4, 5, and I have my name, Joe, and then I have my supervisor ID, and I have 2, 3, 4, 5, 6, and then I have 98765, and I have Mary, whose supervisor ID is 2, 3, 4, 5, 6. Then I have 2, 3, 4, 5, 6, and that's Alice. Her supervisor is 8765. I'm just trying to make sure it's nothing I already have. You see the relationship here? What does this tell you about Alice? Who works for Alice?
Alice, Mary.
Mary. Anybody else work for her?
Also Joe.
Joe. So Alice is like, let me just redraw this thing here because this was confusing. I did it so poorly. 2, 3, 4, 5, 6. That's easier to see now. Alice's employee ID is 2, 3, 4, 5, 6, which is also her when she's in the capacity as supervisor. That's her supervisor's ID. So Joe and Mary both report to this supervisor ID, which happens to be Alice. That make sense? And then whoever this person is isn't on the list yet. But everybody's got a supervisor, and this shows that Alice has 2 people that work for her, and each one of these people has 1 supervisor. In our case, Alice has so the cardinality for that works this way.
But could it be seen as a way like a person has superior and also superior? The boss's boss can order around everybody.
Right. So if I put another person in here, who does Alice work for?
For William.
She works for William because her supervisor ID, 87654, is also William's employee ID. See how this goes? This is one of the coolest relationships, the recursive ones. I remember when I was as a student, the first time I saw one of these, I just sort of stared at it for a while. I went, what? What is this? How does this work? This can't work. No way, can't have it. Can't have a table recursively pointing back to itself. Yes, you can. Believe it or not, yes, you can. And that's the way it works. Right there, that's the data. And so you would, if you were going to create a query and access like this, you'd have 2 copies of the same table on the query screen, the relationship screen, and you would click on one, draw it to the other, and it would work. I think that's about all I needed to cover. Let's just make sure. And then get into this design one. This is an example that they use. Any questions? How are we doing? I will tell you, it does take a little practice getting used to the crow's foot notation. Let me go back to that slide. Where is it? Where is it? Oh, there it is. Ding. This here. Become familiar with this. And the way I do this, if I have entity A, right, and then I have entity B, regardless of what they are. if I have a relationship that looks like this, and this is common, what this says here is that if I find information about A in here, when I use my relationship to come back here, how many of A should I find over here?
One.
One and only one. Right? This tells me if I find information about A over here, I come back, I find one and only one. And if I have information about B over here, how many times can I find it over here?
Multiple records from B.
Multiple records from B. And what about the minimum?
Minimum, likely one.
Yeah, I have to find at least one, but I could find many, right? Make sense? Just the way I learned it was if I saw the cardinality and I'm looking over here at this, I go over here and say, all right, if I have information about B in here, what does that give me over here? Especially when I'm trying to figure out, you know, what entity C is, and I know C is going to relate to B. And I go, all right, if I find information about B over here, how many does it go over here? Well, I'm going to say many here. Minimum, it might be 0 here. And if I find something, and this is kind of getting ahead of ourselves a little bit. If I know something is like the primary key in this, in C, and I find it over here as a foreign key, that makes it pretty easy. Because if it's a foreign key over here, I know when I come back over here, it's going to be 1 and 1. And when you're kind of designing this thing out, sometimes as you get more experience, you get more comfortable with it, you kind of know how things are going to relate together and say, you know, I've got a schedule table over here, and I've got a courses table over here, and a student table over here. All right, I know the course ID is going to be in the schedule. All right, that course ID is unique over here. So coming this way, one and only one. And course offered multiple times or not at all, many and 0. So this is so this would be the optional many on this side of B, the mandatory 1 on the other side for C. Between A and B, you have the mandatory 1 on the A side, and on the B side, you have the mandatory many. Still haven't figured out a good one for the optional one. I don't know. But it's out there. Any questions? But I would, even if you had to, go so far as print out this page when you're doing ERDs, and just, you know, to give yourself something to go back and look at.